back with Dr. Fall. And now we're going to talk about anomalies for ionization energy and affinity energy.
Electron affinity.
Electron
First,
affinity.
you have to define what electron affinity is.
It's
Okay, the one thing we forgot to mention from the last video is that
I did it.
ionization energy is when you remove, is the energy needed to remove an electron, so you're adding positive energy.
Yeah.
Electron affinity is energy you use to put in an electron. Sometimes it's positive, sometimes it's negative. There, like for example, the halogens part of the periodic table, which is from fluorine down. You see it from fluorine down, like all of this, right? From fluorine down, this is called the halogens part of the periodic table. So this is really close to the noble gas configuration. So you really want to gain one electron, so it's highly positive. The electron affinity. Electron affinity is basically the tendency of an electron to gain an electron.
So it's very high. Fluorine.
Yeah, because if it was
look bad.
Okay, so if it was in the noble gas configuration, it would be highly positive because it really does not want to get that electron.
Yeah, it doesn't want to.
Yeah, but if it's in the hydrogens part, it really wants to gain that electron, so it could be close to the noble gas configuration.
The same as this column. What's happening? Okay, so this column too, they want their electron affinity.
You mean the other one?
The electron affinity
you mean
is
this one?
greater than 0. It's positive because they already have because their configuration is already perfect. Because they're like for BE.
It's not perfect. It wants to lose 2 electrons, so it'll be close to the noble gas configuration.
2. It's ending, so it has a perfect orbital. It doesn't want to gain the p orbital, so it does.
So let's talk about the anomalies for ionization energy. Because usually the trend of ionization energy is that as it moves to the right in a row, usually the ionization energy increases because the radius becomes smaller, and thus if the radius becomes smaller, that means it's harder to take away an electron from the atom. And as you move down in a column of a periodic table, usually the radius increases, so the ionization energy usually decreases because you're at a higher n value. So the higher n value, the more excited you are, and the more the electrons, like, easier it is to remove an electron from the atom. Right? So we know this. So this is the trend of a periodic table. For a periodic table, but like for example, for every rule, there's an exception. As you move from nitrogen to oxygen, instead of the ionization energy increasing, it decreases. Well, because let's write the electronic configuration of nitrogen. Electronic configuration of nitrogen is 1s2, 2s2. 2s2 and 2p3. And for oxygen is 1s2, 2s2, 2s2, and 2p4. 2p4. So basically everything here is the same, so we could just ignore this, and we can analyze the outermost part. So basically the outermost part is a p orbital. It's a p subshell which has 3 orbitals inside, right? And this one is also a p orbital which has, this is a p subshell which has 3 orbitals inside. This is what you like. So this would be up, and up, and this would be up, and down. So usually you have these for, like, an electron is stable in an orbital if If an electron exists by itself in an orbital, that means it does not want to repel any other electron because there's no other electrons in the orbital that repel. But if you have two up electrons, both they're like in the same orientation, they would have a repulsive force against this down electron. So this would be really easy to get rid of this down electron in this part of the orbital. So since it's really easier to get this down electron away than to take away one electron from a full orbital, from a full subshell, then that means the ionization energy of oxygen is less. Thank you.